Correct.
The math is happening on the middle three boards. Are you sure I cannot use this one? Maybe I shouldn't.
You can.
No, no.
But not so clear.
Okay, okay.
You can, but it's not one.
When I'm obedient, I'll start when I'm told to start.
Yeah, that's a good attitude.
Isn't it better, Musa, if you switch the light off on the network? Do you want me to try?
No, I think we already found the optimal,
Okay.
light configuration. But if you wanted to dim lights?
No, I mean, for me, it's fine, but
Mhm.
I think for Zoom, it's better without the light on the blackboard. But if you find your solution, there is
No,
no.
I think now it's a good compromise. Like, somehow it turns out that this combination.
Actually, without the light at all on the blackboard might be better, right? Part of the problem, because before.
Sure, it's better for the Zoom. It's worse for us.
Okay.
Yeah,
Okay.
yeah, that's true.
Okay.
All right, people, welcome to this morning's session. And yeah, the first talk is by Bar-Natan. The title is Secondary Operations, Emergent Knots, and the Goldman-Turaev Lee by Algebra.
Okay, thank you. Muse, are you recording?
Yeah.
Good. So I have to say this is my first Blackboard talk in a long, long time. So I'm a bit nervous. Also, the talk today, apologies, the talk today is mostly language. And like the meat, sorry, tofu, is in my talk on Thursday, which is on a completely different topic and actually unrelated to this workshop. So my goal is mostly to introduce emergent knots, and the purpose is to make Yusuke happier for his talk. But I think it's actually closely related to what people from the Geneva group are going to talk about tomorrow. So, so maybe it's not just that. Anyway, let's start with secondary operations. So I want to tell you that the Goldman-Turaev operations are in some sense secondary, and that's not an insult, it's a technical term. So a secondary operation is, suppose you have two primary operations whose symbol, so whose highest level term is the same. Then the difference between them is somehow lower order stuff, and that's a secondary operation. Okay? So let's convert it into a commutative diagram. So suppose you have 0 goes to A, goes to B, goes to C. You know, let's add a 0 here, even though this 0 is not used. And this means that B is kind of the big space. And if you mod out by A, you get C. So C is somehow the top level stuff, which if you ignore lower order stuff, then you know, if you ignore the lower order stuff, namely the A part of B, then you only see C. So now, suppose you have two operations. So let's call them lambda 0 and lambda 1, mapping E into B, E in some other space. And suppose the difference when you map into C was equal to 0. So one way to say it is to say that you have a map going this way, such that the two triangles that you see here are commutative. Okay, then obviously, since the difference goes to 0 here, it means that the difference came from here. So you get a new operation, eta, which is lambda 0 minus lambda 1 going from E to A. Okay? And in fact, I didn't really need it to be two operations. I could have had just one operation such that the composition into C is equal to 0. But in all the examples, it will this one operation will be the difference of 2. So I'll write it this way. Okay? Okay, let's fancify it a little bit. So suppose the top layer was itself a quotient situation. So suppose we had D goes to E, goes to F, goes to 0 as the top layer, and the bottom layer was A goes to B, goes to C, and coming from 0. And suppose I had two operations, lambda 0 and lambda 1 going from E to B, such that you could make a commutative diagram like this. And by the way, these two operations sometimes would be coming from two operations going this way. So lambda 0 bar and lambda 1 bar by simply composing. So like my input will either be two operations going from E to B or two operations going from F to B, in which case I create the two operations going from E to B.
So the commutant squares, they commute for both lambda
Yes.
naught and lambda 1?
Yes. Okay. Well, in this situation, so again, if you have something in F, then it came from something in E, you push it down to B in two different ways and take the difference. It pushes to C into C to be 0, therefore it came from A. And if you recognize it as the construction of the connecting homomorphism in, it's very similar to how the connecting homomorphism is defined, but it's a slightly different context. And I will call this thing, God, I don't know where to draw it. I will call it eta. Okay? So eta is the secondary operation going from F to A. Okay. Okay. The next thing that occurs when you talk about the connecting homomorphism. So the next thing that you learn about the connecting homomorphism is that it's natural. So if you have a map between complexes, the connecting homomorphism on the kind of commutes with the map between complexes. Yeah.
Sorry, so the fact that the difference between lambda naught and lambda 1 maps to 0 in C, that's the condition, right?
Yes, yes. Oh, did I call it lambda 0 and lambda 0? Yes, I did. I meant lambda 0 and lambda 1. Okay. So now suppose I had a second layer. So suppose I had D prime, E prime, F prime, A prime, B prime, and C prime, and suppose they made the same picture among themselves. Did I miss any arrows? Maybe not. And then suppose also I had vertical arrows. So this going a map from A to A prime, a map from D to D prime, a map from E to E prime, B to B prime, C to C prime, and F to F prime. Sorry, it gets complicated. Then I claim that if all, Then, first of all, since the lower diagram is the same shape as the top diagram, I also have a secondary operation, or if you want, a connecting homomorphism eta prime at the bottom diagram. And I claim that if all of the vertical squares commute, then the square formed by eta and eta prime also commutes. So going from f via eta to a and then to a prime is the same as going from f to f prime and then via eta prime to a prime. Okay, so let me say, so this is, let me write it. So this is naturality if all a priori given squares. So if all the given squares commute, then so does the square produced by the secondary operations. And yeah.
Sorry, just one more question. So this, you say it's not quite a connecting homomorphism, but if you say that your map is actually lambda 0 minus lambda 1 because they don't seem to appear separately.
Yeah, I said that at the beginning. I mean, in applications, it's always lambda 0 and lambda 1. Also, you know, if I wrote it as the difference, then I'd have to say that the condition is that when you go to C, you get 0, right? And if I make them separate maps, all I have to say is that the square commutes. So like I save 3 words or so. Okay? But sorry, but what was your question? I interrupt.
No, but then if you look at lambda 0 minus lambda 1, it is the connected homomorphism construction or not?
I actually didn't even fully think it through myself. So it's very similar. Okay. Okay, maybe it is. I just didn't think it through. Okay. Now, in the examples, the top layer will always be knot theory or some variant of knot theory. Knot theory is always graded, or not graded, filtered. Sorry, there is a filtration, the finite type filtration. And then you can take the associated graded. So the lower level, so the top level will always be knots. The lower level will be always the associated graded of knots, which is often called A or core diagrams. And so this is a functor. Taking the associated graded is a functor. So if you have a diagram at the top, you automatically get a diagram at the bottom. You do not automatically get morphisms from the top diagram to the bottom diagram. That's an expansion. An expansion is precisely, again, so the functor takes the spaces, kind of takes the category of spaces to the category of to a category of spaces. So you get the diagram becomes the diagram, but there isn't a map between them. But then if you get an expansion, so a Kontievich integral, so a map between these two diagrams, then you get a commutative square, like commutative picture like this. And then the connecting homomorphism here, the connecting homomorphisms at the top will be the Goldman-Turaev operations. The connecting homomorphisms at the bottom will be their algebraic counterparts, their associated graded, and the fact that the diagram produced by eta and eta prime is commutative will be the homomorphicity of the expansion of the Goldman-Turaev expansion. That's the plan. Okay? So let's start defining. So I guess this was part one, and now part two. Let me talk about emergent knots. So emergent knots in a surface cross an interval. And I should say that often the surface will be a disk minus n points. So disk minus n points. And then sigma cross an interval will be basically this thing made three-dimensional. So a room with n vertical lines removed. And this is what in previous talks, in the previous talk that I gave on the topic, I gave only once before a talk on the topic. It was 2 years ago in Le Diablerie. So 2 years ago, I called this the pole dancing studio, right? So this is PDSN, namely, again, a room with n vertical bars removed, and knot theory happens inside this room. So kind of the knots are the dancers in the pole dancing studio. Okay? So let's make a bunch of definitions. So first of all, let K of S be knots in sigma cross I. I'll fix sigma once, I'll fix sigma, and later I will furthermore fix it to be this particular sigma. Okay, so it will not be a part of the notation. If you insist, you could add here a subscript, I don't know, a lower subscript, left subscript sigma to be clear which sigma it is, but I mean, for me, sigma will be fixed. Okay? So, sorry, I'm running out of chalk. Okay. So, so K of S will be knots in sigma cross I with a skeleton S. So let me explain what I mean by skeleton. So the skeleton is basically the thing that gets knotted. So it could be a line, it could be a circle, it could be a circle and a line. And more precisely, if it's a line, I should indicate where its end points are. So, for example, if the arena is a pole dancing studio, so these vertical lines stands for the poles, then the skeleton could be a loop, which means that the loop could be knotted with anything, or a line, but if it's a line, then maybe I'll indicate that it starts here and ends here, or maybe it starts at the top and ends at the bottom. And then to separate the poles from the thing that actually get knotted is I'll indicate these with the letter S. So S stands for strands, and also these are pieces of the skeleton, and they are to be distinct from P, which is part of the ambient space, or in fact, they are not part of the ambient space.
So in
So-
the red, they go black and red.
Right, in Le Diablerie, they were black and red, but you know, I don't want to.
The S and
Yes, so P for poles, and they are vertical and fixed and don't move. And S is strands, and they can be knotted. Oh, so they are tangles, really.
They are tangles, but we call them.
I call them knot because it's generally knotted objects. Yes, I mean all type of knotted objects. And in fact, you know, sometimes if I have the right mood, it's not going to happen today, but you know, I could restrict my attention to braids, for example. Okay, so I mean, when I say knots, I mean in the most general sense, knotted objects. In fact, they could be graphs, okay, but things that you could knot, okay? But let me make one correction. I'll always take linear combination of things like this. So, and let's say the ground field is over Q, over some field of characteristic 0, but I'm not sophisticated, okay? Just Q, okay? Okay, so this is the first definition. K1 of S is the same, except, well, not the same, but it's the span within the previous space K of S. So with the span within this, or you know, if you wish, you can call this K0 of S, and then this will be K0. The span within K0 of nodes with one SS double point. So an SS double point is a point in which two strands cross each other, go through each other. But this is not a knot. Okay, so this really stands for, it's really a mnemonic for, it really represents an overcrossing minus an undercrossing. Okay, so this is kind of like an augmentation ideal within K. Okay, and similarly, K2 of S will be the span, basically everything is the same, except that with two SS. Oh, sorry, when I say SS, I should have indicated both of these lines are strands, not poles. Poles cannot cross, poles are fixed. But I'm not looking at strand-pole interactions, only at strand-strand interactions at this point. Okay? So K2 of S will be the same thing, but with two SS double points. And this is to be interpreted as a difference of differences, right? So like this expands to over minus under, this expands to over minus under. So this is like a linear combination of four things. Okay? Then K slash 1. So K slash 1 is defined to be, and now I'm dropping the S just because I'm lazy. You fix a skeleton or you indicate what the skeleton, but I'm dropping it for this. So K sub 1 is K modulo K sub modulo K1. And let's give it another name. So you see, what happens if you mod by 1? If you mod by 1, then basically I mod by these things. So over becomes equal to under. So the knot got ghosted, became a ghost. Not in the sense like on Tinder when you get ghosted, but in the sense of ghosts can pass through each other without, you know, they just walk through each other. Okay, so I will call it K ghosted, but K ghosted is really homotopy classes. So basically it's homotopy classes of curves inside our arena, meaning maybe a pole dancing studio, maybe some other surface, with where the endpoints of the classes are specified, or some classes indicate stands for curves, closed curves. So, for example, so really this is homotopy classes. So really, if you look at K ghosted with the skeleton, a line, and a circle, then this is the same as the fundamental group. So the line indicates an element of the fundamental group. Tensor, so I'm allowing linear combination, so it's really the group ring of the fundamental group. When I write pi1, I always mean the group ring. And these are elements of the fundamental group without a base point, which is the same as cyclic words, or the same as conjugacy classes. So tensor, what people here denote with pi1 with absolute value, and that just means conjugacy classes of elements of the fundamental group. And maybe I'll also say that there is also a framed version. So I could have talked about framed knots instead of ordinary knots, and then there will be a framed version here, but I'll skip that. Okay, so I think that's all I had to say about ghosts. Okay, and now somehow the central definition. So K mod 2 is is defined to be K mod K2, and I will call it K emergent. So EM stands for emergent. So what do I mean by that? So like, had I modded out by K1, I would kill knotting. So K ghosted, knotting gets killed. Here, knotting just nearly gets killed, but not quite. So basically in K emergent, if you look at the difference between an overcrossing and an undercrossing, then after that, you can take further differences for free. Okay, but the first difference counts. And the origin of the word is like my understanding of the French language. So I have an emergent understanding of the French language, which means it's not zero, but it's very, very close to zero. Okay, so this is knotting, emergent knotting, very, very little knotting remains. Okay? So, I said before that like secondary operation is not an insult. Emergent knot is sort of an insult. It's barely knots. Okay, good. Right, and maybe from now on, let's make it official. So sigma is equal to a disk minus n points. So meaning that our arena is the pole dancing studio with n poles. And let me give you a few examples. Okay. So example number 1 let me take the skeleton. So, I already specified what's the arena, so I just need to tell you what the skeleton is. So the skeleton will be two circles uh, marked with 1 and 2. Oh, sorry, even before, I should have said in general. So before I had, like when describing secondary operations, I had A goes to B goes to C. Okay, so just to be clear, my A goes to B goes to C, A, B, C, or D, E, F will always be emergent nodes in the middle. They map into ghosted nodes, right? And they come from, so everything in K up 1 maps to 0 in K ghosted. K ghosted is K modulo K up 1. So the kernel is K up 1, except things in K up 2 map to 0 already in K emergent. Right? K emergent is K modulo K up 2. So I could mod out by K up 2. So this is the space A. I will short this with K up 1 mod 2. And my operations will go from KGH to K1 mod 2. And these look like completely different spaces. But later we will impose a further relation, and then they will become isomorphic. And then my operation, the operations will go from homotopy classes back again to homotopy classes. Okay, so let's do the first example. So the skeleton is this, and then K GH. So now I'm writing what used to be F. So the domain of the secondary operation. So KGH of two circles is really, two circles is really two homotopy classes. So pi1 tensor pi1. So two close homotopy classes, so two conjugacy classes in pi1. And then let's complete the diagram. So this gets a map from K EM of two circles. And now I need to construct two maps, lambda 0, or maybe I'll call it lambda 1, 0, and lambda 1, 1, because this is the first one is, for example, 1. Okay. So, and they also go into K emergent of two circles. But let me tell you what they are. So, my input is a node with two components, right? My output for via lambda 0 will be you put the two components, you stack them vertically with the first component above the second. And lambda 1 will stack them vertically in the opposite order. Okay, so lambda 1, 0 is put 1 above 2, and lambda 1, 1 will be put 2 above 1. And if you want a picture, so here is the pole dancing studio. So if the two components are red and green, then in one map, red is re-embedded on top of, sorry, green is re-embedded on top of red, and in the other map, the order is flipped. Okay? Now,
Maybe like if it's clear, but maybe just as a matter of definition, at the top row, K emergent, right? With two circles.
yeah,
They are in principle, they were already positioned in some way, right?
yeah, so I'll reposition them.
Oh, okay, so you whatever, like forget how they
Yeah.
were positioned.
Yeah. So, or alternative, again, really my map.
In the end, yes.
Yeah.
Yeah, but like.
Yeah. And then clearly, well, you can this. I mean, here you get KGH of two circles, and the squares commute because once you because modulo homotopy, it doesn't matter which one is on top and which one is below, and basically you can slide them through each other. Then this gets a map from K, so I'm writing not the full diagram, only the parts that I care about. So K1 mod 2 of two circles. And let me just interpret this. Okay, so K1 basically is maps of a a skeleton that has one double point in it. So it's or can be spanned by maps of a skeleton that has one double point in it, and this which really you can think of as a knotted graph. Okay, and then so if I'm thinking of this as being generated by maps of a skeleton that looks like this, then after I've mapped this into the arena, the ambient space, I mod out by having by two. So basically, these pieces are now homotopy pieces. Okay, so this can be interpreted as maps of a figure 8 into the space, and you can also write it in terms of pi1, but I won't. It's just a basically, well, I'll just stick with it as it is. So this is up to homotopy. So basically, the space like this space is the space of knottings of things like that into a pole dancing studio modulo homotopy, and our secondary operation is an operation that goes from pi1 tensor pi1 into maps of a figure 8. Yes.
So you mentioned like those double points, then they're only between different components.
Sorry?
Like the double points that you only allow them between different components, not one component. Because otherwise you would also get that only one of the loops gives you the figure 8 and you have another one that doesn't.
So I think you are okay. So to be precise, you are right. And this will come up again a few minutes later. But within the difference of our lambda 1 and our lambda 0 and our lambda 1, only only double points of the type that you indicate occur. So you're right, strictly speaking, this space is bigger, but our eta, its target is the subspace in which the double point is between the two circles. Okay? And this will occur again in a few minutes. Thank you. And let's do example number 2. So, example 2. So now the skeleton will be basically this. So I mean, so what I mean by that is that we will be talking about knottings of intervals in a pole dancing studio, where the interval begins and ends at the bottom in 2 specified points. So the diagram.
So, I know it's obvious that over all those vertical arrows that K2 is not to K2, but why is it obvious? I'm kind of a little bit lost in that.
Sorry.
You want to highlight two vectors lambda 0 1 and the ones as well defined. So
Yeah.
So this any row is not sort of each other. It should be an operation which sends K2 into K2. So it's well defined on the course. So
Yeah.
I guess it's totally obvious that it sends K2 to K2, but I fail to see it. Is it okay?
Gee, I hope I didn't get something wrong.
No, I'm absolutely not implying any kind of.
K2. You know, it's possible that I was a bit too ambitious. Sorry, it's possible that I said it wrong. So maybe I should have just kept it, or maybe here the space should have simply been K emergent of a loop tensor K emergent of a loop. So I mean, I'm not sure if I'm not sure if what you said
It might be true.
is a problem, but this definitely solves it. Okay. Okay. So example number 2. The skeleton is this, and then my spaces are K ghosted of this, which is really pi 1. There is a map into it from K emergent of the same skeleton. I need to construct 2 maps into, well, here it will be again K emergent of the same skeleton. And I need to construct 2 maps, but like I indicated before, it's actually easier to construct them going this way, and then these 2 maps will simply be the compositions. And the 2 maps, let's call them lambda 2, 0 and lambda 2, 1, will be the ascending embedding and the descending embedding. Namely, so if you have an element of the fundamental group, you can always, so maybe I'll just write it, lambda 2, 0, the ascending embedding will look like this. So if you have an element of the fundamental group of the complement, so basically the free group, you can first of all embed it as as ascending braid, and then drop down to 0. Or you can embed it, so lambda to 1 will be you first shoot to pretty high up, and then you embed it as a descending braid. Okay? And then, so this generates two maps going this way, but again, that's automatic. And then there is a map into here from K1/2 of a single curve. And like before, this is really homotopy classes of curves like this that have one singularity. So curves that look like this. So homotopy classes of curves like this into the pole dancing studio. And again, modulo homotopy. And this is, no, that's my output. Okay, so these are the two examples. Now I want to get it even closer to Goldman-Turaev. So I'll introduce some new spaces. So now this is part 2.5 of the talk. So let me indicate by K sub H. So again, this could be in any pole dancing studio or any other surface, and with an arbitrary skeleton, but I'm writing the general definition. So this is defined to be a power series in a variable B. In fact, it's kind of irrelevant that it's power series. I mean, polynomials, if you wish, in a variable B. Tensor the old K, except I take B to have degree 1. So, or filtration degree 1. So if I will be writing K up H modulo 2 or up 2, it means I either have two B's and an arbitrary element of K, or one B and an element of K1, or 0 B's and an element of K2. So B has degree 1, and I mod out by a relation, and the relation says that a double point, and a double point really stands for over minus under. So if you have an over minus and under, and of course everything here is strands, then this is equal to B times you replace it by a smoothing, and the H stands for, this is like the relation in the Humphrey polynomial, though it's also the relation in the Conway polynomial, so maybe it should have been sub C, I'm not sure. Okay, that's a bit of choice what to call it. So now, by the way, K sub H ghosted, I mean, here, basically you kill by the image of B. So nothing gets, you've changed nothing. This is just K ghosted. Okay, but there is a nicer theorem or proposition. So proposition, if you look at the map multiplication by B, So B hat, like in quantum mechanics, this means multiplication by B. So if you look at the multiplication by B map, so this is a map from K ghosted. You know, you can mod out by H, you don't have to mod out by H, it's the same as I just indicated, into K. So basically, if I start with K0 mod 1 and I multiply by B, I land in K1 mod 2. So this is a map into KH1 mod 2. And even before stating the proposition, I'll tell you why I care. I care because this is where my target space for the connecting homomorphism, sorry, the secondary operations lands. So the plan is to take the previous examples, the previous two examples, and mod them by H. And the point is that now I will have an identification of KH. So the theorem is that this map is an isomorphism. So basically, KH1 mod 2, which is my target spaces, is simply homotopy, is ghosted knots, which really means homotopy classes. So I get maps from homotopy classes to homotopy classes. Okay? You know, sorry if you're totally bored. I mean, some of you have seen this, and it's just the same as what I said 2 years ago. I admit it's the same as what I said 2 years ago. Okay? Anyway, so let me prove this. So proof. So basically, surjectivity is obvious. So element in K1 are differences. Right, K up 1, they're differences. Anything which isn't a difference is an image of multiplying something by B. So surjectivity is obvious. So all I need to do is to construct the map going the other way. So I need to construct a map psi going the other way, which will be a one-sided inverse. So I need psi such that if you first multiply by B, so do this, and then apply psi, so then apply psi, then you get the identity. Okay? So I basically need to define psi on the, well, I need to define psi on this space. This space is a quotient space. So I'll define it on the generators and check that it satisfies the relations. So psi, I need to define it on things which look like B times something. So if I have B times a naught, I will simply map it to the naught. Right? Basically, B hat is multiplication by B. I need to divide by B. Like the inverse should be division by B. So, or like division by B. So if you have B times a naught, I'll map it to the naught itself. And if I have, so B, this is B to the power 1. If I have B to the 0, so if I have a generator in which the coefficient is not a power of B, is not B, then I will do something fancy. I will map it to 1/2 times the sum over all the crossings in K. So X in K means crossings of K. Now each crossing in K has a sign according to ordinary knot theory. So I'll take -1 to that crossing, and then take that, and then take this K, but with the crossing replaced by a smoothing. And then you have to check things. First of all, you have to check that this map respects Reidemeister 2 and Reidemeister 3. And these are routine checks. You basically, you write Reidemeister 3 and you write with crossings. This is, I wrote it unsigned. You write Reidemeister 3 and you just apply, it becomes a sum of 3 terms on the left, a sum of 3 terms on the right, it checks. Likewise for Reidemeister 2. And finally, you have to check that it satisfies H. But basically, the right-hand side gets mapped to erase the B. The left-hand side, this becomes 1/2 of a smoothing. This becomes minus 1/2 of a smoothing, and it's equal. So this map is an isomorphism.
So
Yeah.
like this check with Reidemeister moves, as we discussed, it probably somewhat similar to what you do checking these Goldman-Turaev operations.
Yeah.
Right.
In fact, yeah, this is exactly the so the fact that the Goldman-Turaev operations are well defined follows from this. Okay.
But sorry, I'm a little lost. Whether this is a 2-dimension, you need to check it on 2-dimensional or 3-dimensional. This random smooth. I mean, it's only,
This is 3-dimensional. I was just lazy. All of these are crossings.
no, but for the Goldman-Turaev is actually only on the surface, right? You check the kind of random moves only on surfaces.
Right. But
But
this implies the fact that the Goldman-Turaev is well defined.
Okay, implies.
This is something else,
Okay.
but it implies.
No, but when you check it,
And-
the target is ghost, but ghost is not very 3-dimensional,
Yeah. So, yeah, I agree.
right?
Yeah.
So it is actually 2-dimensional, the ghost, because
The target is really 2-dimensional. Yes, I agree. Okay. So anyway, I'm kind of running out of time. I'm not just kind. I'm running out of time. But let me say, so let me just let me quickly complete the story and then move on. So this is isomorphic via multiplication by B with K GH of, okay. So here I was a bit loose. Here I didn't indicate the skeleton. And in fact, the map side changes the skeleton. Also, the relation changes the skeleton. The relation does not fix the skeleton. So, here it's unclear what skeleton to write. But in the particular case that we have, lambda 0 minus lambda 1 ends in the image of one specific skeleton. So I can restrict my attention to this one specific skeleton, and it's a single circle. And the single circle here is a K ghost of one circle, even if you mod, sorry, so I should mod out everything by H. And the ghost stuff doesn't change. The emergent stuff does change, but the ghost stuff doesn't change. And this is just pi1, and this is the Goldman bracket. And exactly the same over here. So this is the image via B of the map from K ghost of one line in the circle. And this is, sorry, and I have to add H everywhere. And this is pi1 tensor, pi1 absolute value. And this is the so-called, what is it called? The coaction. The coaction map, which is the precursor of the Turaev co-bracket. If you want to get the Turaev co-bracket, you have to close this as well and anti-symmetrize. Okay. So I'm, oh my God, I have 0 time left. But now I should be going to part 4.
It's a
So,
little bit negotiable, like how much time would you need?
so, no, too much. Uh, so, I mean, so I'll just say, in principle, all you have to do is to apply the Ger functor. Right? So if you apply the Ger functor, you get, I mean, you get everything becomes algebraic. And maybe I'll just tell you what is the output of the Ger functor. So basically, K of a skeleton becomes, so this is becomes, not maps into, becomes A of a skeleton. So for example, if the skeleton was this, then A of this will be the space of so-called chord diagrams. So the chord diagrams will have a number of poles, because we're still in a pole dancing studio, and a skeleton, a copy of the skeleton, and then the chords will be going, well, no chords between the pole because the poles are stationary, but you have chords going from this to this, okay, from skeleton to skeleton, from strand to strand, and from strand to poles, and then you'll have a few relations. So basically, if you want to ghost something, the ghosting relation is if you have a chord between two strands, you're equal to 0, and that also the same as saying, or also B is equal to 0 if you do the B extension. Then there is the emergent relation. So the emergent relation is if you have two chords between strands anywhere, like I wrote them in a certain way, but I mean anywhere, going from any place to any other place between two strands, then this is equal to 0. Likewise, B squared is equal to 0. Also, B times one chord is equal to 0. And finally, there is the H relation, and the H, oh, sorry, I should have said even before that, you have to mod out by the usual 4T relations. And then there is the H relation, and the H relation says that if you have a chord between two strands, and it's more fun to draw them with opposite orientations, then this is equal to B times the strands replaced by a bridge. And so this is the emergent relation that Yuske will be talking about in a completely different language, but still it's the same relation in his talk. And I believe it's also very similar to what people from Geneva have been playing with. So they maybe will be telling us about it tomorrow. And I think what I don't have time to do, and I genuinely don't have time to do, is to tell you how if you repeat these stories using A instead of K, you get the Goldman-Turaev algebraic the algebraic counterpart of the Goldman-Turaev operations. And furthermore, if you use the Kontsievich integral, then, well, for the Goldman picture, all the vertical arrows are make commutative squares, so you get the homomorphicity of the secondary operation, meaning the Goldman bracket. And for here, not quite all the vertical lines are homomorphic, not quite all the vertical squares are commutative, but when they're not commutative, they're not commutative in a controlled way. And then you can check that if you map this further to pi1 tensor pi1, so it will close the remaining open component, then it becomes well-defined. Then all the commutativities do hold. So everything works. And I have to say, I have to make two comments before I quit. So I'm already 5 minutes over time. So one is, I'm not happy. So I still think, I feel that, I mean, I don't know, I hope this was clean, but at least the last bit here can be cleaned even further. We haven't cleaned it, but my feeling is that it should be possible to clean it even further. And the second comment is that it's not a comment, it's a homework assignment. So homework, do the same for W knots and W core diagrams. And the point is that this should, like the expansion in this case, would be coming from Kashiwara-Verne. And so this will relate, or this will re-relate Kashiwara-Verne to Goldman-Turaev. And it's not trivial. I mean, it's not just do the same. I mean, you have to think more carefully. What are the relations? What is H? What replaces H? How to replace this? What to replace the spaces by? So it's not trivial. It's a serious assignment. I mean, like it's a term project, not just a next week assignment. Okay, and I'll stop.
Thank you. Any questions or comments?
Yeah, two small questions. I mean, suppose you only have one punctures, you have one line,
Yeah.
and you have a circle.
Yeah.
I remember in your old paper, you could explicitly compute the conjugate integral of this, right?
Yeah.
But I feel for the other generators, could you compute the conjugate integral explicitly? I feel the generator is relatively easy for this kind of punctured
So
plane.
I have not. I've done some explicit computations, but not enough. And maybe, possibly, Yuska will mention something I don't know. But bear in mind that all of this is happening in emergent knots, and in emergent knots, they're barely knotted. So you kill quite a lot. Like basically, you mod out by this relation, and modulo this relation, the computations are easier. So you expect to be able to compute more than just the Kontsevich integral.
But do you think you can kind of explicit compute the conjugate integral of the generators of these scheme modules or this punctured plane?
No. It will remain unexplicit at the end, or written in terms of integrals. So.
Okay. Thank you.
Any more questions? Yeah, so since you mentioned your talk 2 years ago, right? So in that talk, there was also a little bit of a discussion that maybe one can continue. It's like you're looking at K1 mod 2. What about like K2 mod 3? And so on. Would the story repeat in some way, right? Like kind of.
I have not explored.
But what would be your speculation?
I have no. Sorry, I'm really sorry. I have no useful speculations. But my speculation. But another speculation is. So I was a bit ambivalent about whether I apply the H relation or not. Like at the end I did, but before that I had pictures in which I didn't. And I think there is real content here. So I think the Goldman-Turaev operations really do have counterparts in which you end up talking about singular knots, embedding of singular knots. And and that there will be interesting things to say about those. So like this is the direction I'm more happy to speculate about.
Okay. Any more questions or comments?
Yeah, also, I'm a little curious, because in the beginning, you explained these secondary operations with some like exact sequence.
Yeah,
I feel this is very similar to in physics, they always do this semi-classical limit. Right, you take some quantum stuff, you take semi-classical limit. I don't know whether your exact sequence can also explain that all the semi-classical.
no, I don't know what to say. Maybe one more word, my talk on Thursday is totally unrelated.
Okay, well, thanks again. Let's definitely keep the schedule, especially for Yusuke, who will be speaking then in 20 minutes. Is it okay for you people? Okay, so then we resume as scheduled at 11:30 Geneva time. So Yusuke, for you is it fine? So in 20 minutes. I'm not sure he hears me.
Yusuke, are you there?
No, he muted himself.
Oh, okay.
Oh, I'm sorry. I muted myself. Sorry. I hear Draw well, but sorry, I don't hear Anton well. What did you say?
Continue in 20 minutes.
Okay, as scheduled.
Yeah,
Okay.
as scheduled.
Okay. Yeah.
Mise,
Mhm.
will you send me the file
Sure,
or, you know, a link to the file or whatever?
I can.
Thank you.
Right.
Message from the guy, the methods. Yeah.